Can everyone hear me? Is this working all right? Excellent. Okay, so I'm tasked with teaching you about machine learning, and fortunately, my colleagues and I in the past year wrote a really extensive review on machine learning intended for people with a physics background, but it doesn't really matter. And I'm going to be basing these lectures off of selections from that. And I'll try to tell you where we are as we go. Another nice feature of this review is that it comes along with around 20 Jupyter notebooks where you can test out ideas without having to know that much about Python if you don't speak that language. So let me spend a couple of minutes just introducing myself and where we're going. So in case you want to email me, this is who I am. My email address is my name at Gmail. So I have a plan for the set of lectures, but I'm kind of hoping that it doesn't go as planned. And this first one in particular is going to be fairly high level, and I think I've set it up so there's lots of room for questions. I expect this to be an interactive group.
We do questions, right?
Is that right? As the questions turn into a discussion, hopefully, I might find out that your interests are different than what I had planned, and I can change directions for future lectures. But roughly speaking, today I'll tell you sort of the basics of what is a machine learning problem, why it's difficult, why it's not what some people that come from, at least in my experience, come from things like physics think, and then some basic intuitions from what's called statistical learning theory that sort of give you an idea of some of the challenges in trying to learn from data and how to mitigate them. And then we'll do a calculation that's 3 lines long, maybe a couple more, but it has a lot of annoying notation that's better to talk through. I'll mostly not use slides, but I will have some, so I'll put them up there as needed. So one thing before I get started, I want to talk about is most of what I'm going to say in these lectures is about about machine learning as used if you were working at Facebook or Google or someplace where your goal is to make predictions and do that well. Someone tells you what your objective is, and you want to do that well. That's a very different problem than what you're trying to do in science often, which is try to understand your data. And I hope that this can turn into a discussion, but one should be wary trying to use these tools sometimes for developing understanding, because it's often possible, it's almost always the case that you're making predictions with a model that's wrong, and trying to take apart and understand that model can lead you astray if you're trying to understand the data itself, or the process that generated the data. Okay. So I thought I would start with some plots of very high level, an example of trying to fit models to data, fit curves to points, and talking through what's easy, what's hard, what's obvious, what's counterintuitive. So let me do that if I can wake my computer up. Hello. Okay, so actually, maybe I should. Hopefully, that'll stay awake. The easiest possible problem that you could be given is a problem where you have data that is generated from some model that has no noise. So there's some function f of x that creates some points, and you want to fit your points, fit a curve or a line to those points. So this is, I want to emphasize, this is never the case. But sometimes people's intuitions are built around this case, and that can lead you astray, so I want to go through it. So let me imagine a situation where I generate a bunch of points from a line, and then I fit to those points either a line, a third order polynomial, or a 10th order polynomial. If I generate 10 points from this line, and then I fit it, well, I have enough points so I can fit the line, I can fit the cubic, I can fit the 10th order, and they all fit perfectly, right? Okay, great. And then if I take that same line that generated the data, and then I sample new points from it, and then ask the model to make predictions on those new points, all these three models do a perfect job because they reproduced, they found the exact true function that these points were coming from. Okay, great. So this is if you have a secret hidden function which is a line and you generate points. Now if you have a secret hidden function which is a 10th order polynomial and you do the same exercise where you fit a line or a cubic or a 10th order, you find that, well, lo and behold, the 10th order does the best because that was the best model, right? The third order one does better than the line, but not as good. And then when I sample new x points from that 10th order polynomial and look at where they are, the 10th order one fits perfectly.
Okay, but obviously the parameters of your 10th order polynomial and the two examples are not the same, right?
Down here and up here? Yeah. So here, the actual data itself came from some secret 10th order polynomial.
Yeah, but I'm saying the parameters of that 10th order polynomial.
Oh, that you learn are different.
Yeah, I mean, it's a matter of scale. You're basically looking at the first one. Scale where it's linear.
Yeah. So in this case, the secret function was just a line. In this case, the secret function was not a line. So think these two rows are sort of separate. And in both cases, though, in this case, you recover the true function because you were fitting with the right model class. It was a 10th order polynomial that created the points. You fit a 10th order polynomial, so you get it back. And then when you test on new points, you fit them perfectly, or you don't fit them. You predict them perfectly, and you can even go beyond. So here, I sampled points between 0 and 1, and here you can take points from that secret 10th order polynomial and go beyond, and you'll even fit those. So you can go outside of where you were training it, and it works perfectly. So this is an idealized setting, and I want to make sure that this is not what you think is happening when you're trying to solve a learning problem, because you almost are never in this situation. There are two things about this situation that make it unrealistic. The first is that you never have the right model. You always have the wrong model. And secondly, I'm imagining that the data was generated from some function with no noise added onto it. And you almost always are going to have noise that you have to deal with. Does this make some sense? Okay. So now I want to do the same exercise, but now I have noise. So in the first plot here, the actual secret function that generated the data was a line again, but then there was some noise on top of it. And then I asked this line to best fit that data, a cubic and a 10th order to best fit that data. And I'm not telling you the numbers, but if you look at the squared error on the predictions to the points, the 10th order one will do the best because it had more ability to sort of wiggle around and fit that extra noise. But when you go and look at new points sampled from that same function, the 10th order one you can see is doing crazy things at the edges here. So there were no points beyond, say, 0.9 something. So it was happy to diverge down in this direction. So now if I ask it about points over here, either a little bit more than one or even less than one, it's going to make terrible predictions. In this case, the cubic and the linear do much better. And you might say, okay, that's not that surprising because, well, you generated the data with a line with some noise, so maybe the line should do the best. If you do the same exercise like we just did before, but instead of a line, you generate with a 10th order polynomial, and then you add noise. Again, you would find that the 10th order one fits the wiggles of the data the best on the data that you trained it on. But then when you go and you look on the data that you test on, again, this thing was diverging down this way. And the actual 10th order polynomial that generated the data ended up going up this way. So here you had 100 data points with noise, and you might have said, well, I have 10 parameters to fit my 10th order polynomial, 100 data points, I should be able to fit that. But it actually performs terribly. And if you want to make predictions with these three options, probably the third order would be the best. And that's not necessarily obvious, that the true process that generated this data was a 10th order polynomial, and yet the third order one is the one that makes the best predictions of these. So this is, yeah? In this case, this is doing a linear regression, which is convex. So there aren't any only local optima. This is a global optimum. Mm-hmm.
Okay, that take.
How do you tell, like, so you have 100 points in the training set.
Yeah.
Fit it to 100, polynomial over 100. Go through every point. So how do you balance between, that limit where you spend so much time on noise, fitting noise, to the other limits?
So that's what I'm going to try and focus on today. So hopefully in an hour and 20 minutes, we'll have a better understanding of how to do that, or how to think about the different forces that play.
So the point you're trying to make here is that the function that's predictive may not be the true function. The function that's predictive.
Right. It's almost never the true function. And this is in an idealized case where the true function is actually within the set of functions that you're willing to try and fit, which is never the case. But even in that case, it's not the right function. Yeah.
So is this a function of number of data points, sampling of the test points? If you had, let's say, a few samples of your test points that were up there, and that's it, then you would have actually, you might have done a better job with it on the other way. So
Yeah.
there's some amount of data collection and number, the quality of data that's coming in play here.
Yeah. So once you have an infinite number of data points, then you should be able to recover the 10th order one.
Finite, if you had a few points in that direction, you might have done better.
So here I'm training only on points that are from 0 to 1, and then testing it a little bit further out. So there's a sort of domain shift or transfer learning kind of thing. But it certainly is making very poor predictions. You can I didn't plot it, but you can imagine that the true function is doing something like this, and even in this region here, it's doing quite poorly. But yeah, if you had some more points over here, you would eventually start pinning it down over here as well. But so to the point of what happens if you have more data. So this is 100 data points for 10 parameters. Normally, I would be pretty happy with that, right? It seems like a lot of data. What if we go to 10,000 data points to fit 10 parameters? So now, over 0 to 1, we have 10,000 data points. This is the same 10th order polynomial from these plots in the bottom below. And on the training data, now you can see this thing curving upwards. So the function is going upwards. But if you now test it going outside of the domain further, you find that it actually, for some reason, decides to turn around and do something crazy. And this is just to emphasize that even though you might have thought that you had recovered something very close to the true function, because you had 10,000 data points for 10 parameters, this is not the right function. This is not the right 10th order polynomial. And still, in this case, if you really wanted to predict out here, the third order would probably be a better choice. Yeah.
So, I mean, it's not only the amount of data, I think, but also the domain in which you're looking, right? Because X is really small, so a Taylor expansion to the third order, maybe that works quite well with small x. So maybe if you're fitting this thing between like 1,000 and 1,010, maybe it would make a bit of a difference. I don't know.
I don't think shifting it would matter so much here.
But the magnitude certainly does.
The range.
The
You're
range,
saying
I
if you look at have a log scatter of points over a few orders of magnitude, you're less likely to get fooled,
Right.
which is true.
Certainly, yeah. Yeah,
Okay.
sure. Yeah.
So it sounds like in this problem, if you have no idea about the asymptotics of the function, you will never get the right function. But you need some information about what your function does is plus your function does that plus or minus infinity.
Well, not necessarily. So if I go back.
No information outside the bounds outside the data.
Yeah, I mean, in this case, where I had no noise, all I need are 10 points limited from 0 to 1, and I pin down the exact 10th order polynomial, right? But once I have some noise, then all these issues arise. Yeah.
So how much would it improve if you had a noise model for if you added a noise model? So if you assume something about the noise.
So in a sense, this case was constructed to have the right noise model in the sense that it's doing linear regression and minimizing squared error, which assumes Gaussian noise, and we added Gaussian noise. So it kind of implicitly has the right noise model. Yeah?
What is very counterintuitive for me is that, I can see this one, is that if you have, I mean, these are likelihood model, right? So if you have the right parameter, means that your log likelihood is still smaller than with this wrong parameter setting.
Sorry, say that one more time?
I mean, you have a likelihood model, I guess, right? Where you have the likelihood of such kind of fit or whatever.
You can make an interpretation, yeah, of this where that's true.
Yeah, but so it means that the likelihood with the wrong parameters is higher than the likelihood with the correct parameter setting.
Right.
But that's very strange, no?
Hopefully that will be more clear over the next few days. If you maximize the likelihood, then if you don't have a lot of data, you're much more likely to actually overfit to the training set. So you don't want to just maximize the likelihood necessarily.
So not to anticipate, it's like a energy versus entropy problem. So the likelihood is like high likelihood is like low energy, but then you also have the volume of models. That's like the entropy, and that also counts. Right? So
Yeah. I probably
do the calculation that makes that more.
I probably won't do. I wasn't planning on doing that one, but we could.
Okay.
Does everybody know what likelihood means? Good.
Okay. If not, I'll get there tomorrow anyway. Yeah.
So I was wondering, going back to what Antonio was saying, if you're really trying to expand range, can you kind of think of how you should be sampling points in a large range? Like, for example, should you be looking at many decades as in look at 0.01, 0.01? Like, can you make an estimate, or should it be uniformly distributed?
You can imagine doing that in this kind of situation if you have so a couple of points. Oftentimes data is higher dimensional. It's harder to figure out how to do that. Secondly, you often don't get to choose which x's you want data for. You get data, and that's what you have. The question of choosing x points that you want to know the y value is actually an interesting area called active learning, but I'm not going to talk about that for the most part.
Yeah, I guess purely from an information theoretic perspective, it's like, can you maximize by skew backing somehow?
There are things like that you can do, but again, that falls into this field where the data set is chosen by you in a way, which sometimes in science it is. But in the standard machine learning paradigm, you have a data set that your boss gave you, and you need to predict credit scores or something like that. So you're stuck with whatever you have. Cool. Okay, so does this make sense? The lesson I'm trying to like have you take away is that the true model is often and almost always never the best model for you to use to make predictions. And that's well and good, again, if all you care about is making predictions. But if you want to then take apart your model and try and understand your data, you need to be cognizant of the fact that this model that is the best predictor is not the one that is the true process. Okay, yeah.
Very simple question. I don't know anything about machine learning, right? So from this discussion, it's not conceptually sense that when you have a training set, then you get your function or whatever. When you say make predictions, does that mean that you go outside the range of your initial training set, or it could be any? Because it's like interpretation, extrapolation,
Right.
Making a lot and extrapolating.
Yeah. So let me use this as an example. So on this side here, so this was a 10th order polynomial fit to 10 data points with no noise. These were the data points that went into finding the parameters of the polynomial. And then over here, what I did was I sampled different x values and asked about their corresponding y value in the true secret function. And this is the fact that the green curve goes through the points here is making accurate predictions, because these data points were not used to fit the.
But predictions are just any other set of points. It doesn't
Any other set of
necessarily
points.
mean the outside the range
Yeah,
that was made.
exactly. It doesn't have to be outside here. So this is doing both at once. It's asking what happens when you go outside and what happens when you go to just points that were not the ones that you trained on.
But it is a good point that, it seems like the first set is easier than the second. Being outside of the set is the more difficult of a prediction than
Right. Absolutely.
interpolating between. You're not going to get a situation like you had on the next slide.
Yeah, and maybe I was overemphasizing this aspect of it, because most of what we're going to talk about over these lectures is making where you imagine that there's an oracle that generates data for you from some distribution, and the distribution of the data that you're allowed to see to train on is the same as the distribution later that you want to make predictions on. And here it's shifting the distribution somewhat. And that's an interesting and important problem. But in the simplest case, we want to assume that those are the same distributions. Yeah.
So in this case, in the noise case, the likelihood as a function of parameters is, in the noise case, is it very flat? So you have lots and lots of models that have very similar likelihood, and it's very hard to choose the best model. Whereas in this case, it's very peaked, and you just pick the right one. Is that
That certainly can happen, and when we talk about things like neural networks, that is ubiquitous. In this case, because it's linear regression, there's a closed form solution for the parameters that you should choose, and there's as long as you have enough data, there's a unique answer. It could be very flat. So if you're finding the parameters via something like gradient descent, which again we'll talk about tomorrow, then it could take a while if you're very flat. But with linear regression, there's a formula you write down, so it doesn't even know about. You don't need to know about that shape. Cool. Okay, so does this make sense by means of introduction? So the next thing I want to do is give you some intuitions about what's going on in those previous examples, and sort of canonically what happens when you think about fitting models with different complexity, in the sense of 10th order polynomials are more complex than 3rd order, and with different amounts of data. So in the first graph here on the left, what I want to think about is I have one model. I have a cubic or something. And I want to look at my performance, and again, I'm being very vague to start. I don't want to talk about equations right now. I want to look at my performance here measured by, and I'm going to change notations a couple times intentionally because this is in the literature, so you should need to get used to all these. This E stands for error here, and we're going to switch to cost later. So I want to know what is your error on the data that you were able to see to train on, and what is your error when you make predictions on new data from that same distribution but separate samples. And what happens if you have a single model like a cubic and you fit it, there's some secret function, you're generating more and more points from it. What you find when you look at your performance on the data that you're actually training on, you actually find that your error per sample actually increases. The reason for this is when you have very small amounts of data, your model is able to maybe fit those wiggles and do a little bit better. This isn't the case where you have some noise. And then as you get more and more data, you can't fit those wiggles of the noise, and you eventually asymptote at some level of error, which is like the amount of structure in the data that your model is just not able to capture. So you used the wrong model. Both your model didn't have noise in it, or noise is not predictable, and also you used the third order polynomial when it was actually a ninth order polynomial. So there's some finite error per sample at infinite data, and you can imagine that it's reasonable to call this a bias, right? Because you chose a model that's wrong, so it's going to fit certain kinds of structure and not others. And that's the property of the model that you chose, not a property of the data, so it's a bias that you put into the fit. So that's this blue curve. But we don't really care about the blue curve. What we really care about is making predictions on the new data. So what we care about is the red curve, which is your error on the other data that you didn't get to see. The reason for this E in and E out, E in stands for insample, and insample means the data that you're able to fit on. Out stands for out of sample. This is data that you didn't get to see that you're just testing on. And here you find the better situation, which makes more sense, which is that as you have more data, your error goes down. You perform better. And once you reach an infinite amount of data, these two curves reach the same point.
Is this error per number of points?
Per sample, yeah.
Per sample.
Yeah.
And this is a property of the model. Each curve is for one model.
This is for one model, yeah.
With the same set of parameters.
You're fitting different. You're fitting the parameters each time for 50 data points, 100 data points, and so on. Yeah.
Is it always true that E in and E out approach the same value, or is that a universal thing?
If I weren't being recorded, I would say yes very strongly. I'm pretty sure that's true, but I can't think of a case where that's not true. It would be very weird if they didn't.
And is there a way for estimating that asymptotic value, like the value that E in and E out approach? Can you calculate that?
So that's this thing called the bias, which we'll define in equations next. It's certainly possible to make that go down, but as I'll show you on the next graph, that's not necessarily a good thing to do because this only asymptotes at infinite data, and you don't have infinite data. So if you're working with finite data, it's probably not a good idea. Okay. So
But
there.
this is- sorry, this
Yeah.
is definitely not true if you were going outside of the range of like what we were discussing earlier, because like your tenth order polynomial went perfectly through your lines, even the noisy ones. Let's say you have 10 points, so then it asymptotes. There'll be some asymptote, some bias, but then you do the prediction, and now the predictions with that 10th order model were just like way off. I mean,
Yeah.
it seems like
Yeah, if you shift the domain, then all bets are off. That in principle, then anything could happen.
With a failure.
Yeah.
This is like a good case. This is what you want, right?
Yeah, this is for the simpler scenario where you're living only within 0 and 1 always. And I'm gonna stick with that for most of what I'm gonna talk about. Okay. And so I should name a couple of other things. The difference between the out-of-sample error and the in-sample error is how do I want to call it? So I'm gonna call it the generalization error or the generalization gap. And when it's big, that means that you're performing much better on the data that you fit on than the data that you're trying to predict with. And that's a signature that you've overfit, that you fit noisy fluctuations in your data that are not actually predictive. So you would like it to be small, although you don't necessarily want it to be 0, as we'll see. The other quantity, which is the difference between the actual out-of-sample error and the asymptotic value, is called the variance. And that sounds like a very odd name, but we're going to give a context for why that is an appropriate name in a bit. Okay. Any questions on this first? More questions on this first plot? Okay. So this was imagining having a single model and then fitting with different amounts of data. Now we're going to flip it. We're going to have a fixed amount of data, and we're going to look at fitting models of different complexity. And I'm not going to define what complexity means. In fact, one of the great successes of this field called statistical learning theory is like a proper definition of model complexity through things like the VC dimension and whatnot. And I'm not going to discuss that. For the case of polynomials like we just had, imagine model complexity like the order of the polynomial. And we'll imagine like we have a nested class so that a 50th order polynomial is strictly bigger than 10th order polynomial because I could just set a bunch of parameters to 0. So in that case, if you plot these quantities, in particular you plot the out-of-sample performance, which is what you really care about, it's what you get paid for, and then the variance and the bias, again for a fixed size of data, as you change the model complexity, what you generally find is that there is a minimum in the out-of-sample error at some intermediate value of complexity. This was sort of like when we found that the third order polynomial had the best testing predictions, even though it wasn't the true model. And then if you go to a more complex model, you've overfit to the wiggles. If you had a model that was too simple, then you've underfit. And what you can imagine, and should make intuitive sense, is that as your model gets more complex, it can do more things, and therefore its bias should go down. So this quantity, that's the bias, which is the asymptote, should decrease. But what happens is that this other thing called variance actually goes up. And because the out-of-sample error is a sum of a bias and a variance piece, you get a minimum in the middle. Roughly speaking, what variance is, and again, I'll define this for you more properly next, is it's saying if I have a data set of finite size and I fit to that data set, I'm going to, the value of the parameters that I have now depend on the data set. And if I imagine running this procedure many times in parallel universes with different samples of the data set, I'll get different values of the parameters that I fit. And the variance is some measure of how different those parameter settings are from the different realizations of the training data. Does that make sense? Yeah.
Why bias increases against the model?
Yeah. So I want to imagine a situation where, like polynomials, where as I increase the complexity, I make a model that can do everything the old one can do, and then more stuff. And if the bias is supposed to tell me something about like the limitations that of the kinds of structure that my model is able to fit in the data, as I step out and allow it to do more things, its bias should be going down. In the end, if I have infinite order polynomial, then I can fit any number of points, right? Exactly, and then I have no bias anymore. In that case, the problem would be that that would be sort of out at infinity here, and the bias would be down to 0, and the variance would explode, because then the value of parameters I get if I have some finite data set would fluctuate dramatically from data set to data set. Does that make sense? So I want to emphasize that these pictures, I'm going to derive them next, like what these quantities are in the simple case of fitting a model where your measure of error is the squared distance between your model and the data points. But these are generically sort of true pictures for when you fit a model and you define some cost function, whatever it is. These are the kinds of things that are going to happen, and this is sort of the essence of what makes learning hard. It's easy in some sense to fit the training data, and the hard part again is making predictions, and these quantities are supposed to highlight exactly why that is. So one other sort of picture that is useful if you're having trouble making sense of these quantities is, let me imagine a model space in some abstract sense, and the true model is this red dot, and I generate a bunch of data from that true model. It's noisy. And then I fit two kinds of models. I fit a low order polynomial or whatever, a low complexity model, and I fit a very high complexity model. And then I imagine, again, doing that over realizations of parallel universes. And look at what happens on this plot. If you have a very, very high order polynomial, then for one data set, you get a model here. For another data set, you get a model here, and so on. And because it's very high order, it's able to potentially fit the true model class, the true model with the right parameters. But because you have finite data, you're bouncing all around for any realization of the data. So you have very low or essentially zero bias, but your variance in terms of the different functions that you learn is very large data set to data set. On the other hand, if you have a simpler model that can only do the kinds of things in this little region, then it can't actually get to the true model. So it has some bias. It's gonna give you something over here, and different realizations of the data set give you these different x's here. And depending on what you care about, what your cost function is, what kinds of models you have, how much things are fluctuating, it may be the case that you want to work with a biased model that has lower variance, because you end up most of the time being much closer, and it's a safer bet. Even though you know it's wrong, you're sort of hedging your bets a bit, and it's safer. And this is hard for people to swallow often, but it's an important take-home message that oftentimes using a biased model with lower variance will give you better average performance than using a less biased model. Yeah.
So it seems like the variance is going up with complexity. It seems like that should be bounded by the variance of the noise. Because different as you take different from the same take different realizations of the training set, the fluctuations will be just a reflection. The asymptotic fluctuation will be a reflection.
let's come back to this when I actually write down equations for these things.
So you mean the green space is similar to this like graph, and the black space is similar to the other graph in a way? Like analogous?
Let's see. So, so more like this black space here is like a model that's over here, and it's low complexity, so it has small variance. So it's you get kind of the same thing every time, and then this big one is like over here. Is there another question? Yeah.
Slightly related. So is the true model always in some neighborhood of the same like people want, or is it could be totally far off?
Sorry, say this one more time.
Is the true model always in some neighborhood of the low bias ideas, or it could be totally far? Is it possible to bound how far you are from the true model given?
I think if you wanted to bound that, you would have to know what it is already or something, right?
Yeah, but is it reasonable to assume that it cannot be totally far off? So I don't know.
I think.
I'm just wondering. I'm just wondering how far can you be?
Yeah, so I think you can be quite far, and in fact, maybe this diagram is a little bit misleading in the sense that I should draw them both in the case where the red dot is outside of their circles, but one has some huge radius and is centered a little bit closer to the red dot. Or sorry, yeah, a little bit closer to the red dot, whereas this one is centered a little bit further away from the red dot, but is sort of like reliably in one spot. But yeah, it's if you're working with complex data, especially if you're modeling something in biology, it's very unlikely that the true process that generated the data is within the set of of models that you're trying to fit, even in this case. Yeah.
Could you say something about the model complexity, because it's not the degree of freedom that you have.
It's sort of related to that.
Because, for example, I'm thinking the coefficients of a polynomial versus coefficients of like a Fourier decomposition. They predict very different things,
Right.
but they have the same degree of freedom.
Yeah. So it's not exact. It's not equal to the number of parameters, except in certain special cases. But in the case of polynomial regression, it's not a bad intuition to have, that you should think of it like counting parameters. There are examples where you can write down a model with one parameter that can fit anything. So real numbers are uncountably infinite, so I can embed a lot of information in one number. So you're right that I shouldn't just count parameters, but that intuition won't lead you astray if you think about simple cases of polynomial regression. Okay. So I should also mention that for the experiments that I showed you, or the graphs that I showed you a couple minutes ago, those are all generated from the first Jupyter notebook from this review. I should probably tell you what the review is. Now I waited because the title will make sense now. It's called a high bias, low variance introduction to machine learning. And it says for physicists, but if you're not a physicist, that's okay. Right, and so again, so the graphs that were up a couple minutes ago are all from the first Jupyter notebook that is associated with this review. Pankaj Mehta has a website where he hosts these. I think they're not on GitHub, unfortunately. And for some of the questions that everyone was asking, I encourage you to open up that notebook and play with it and change parameters, change the functions, and see if the things that come out are aligned with your intuition. Okay. So the next thing that I wanted to do is a little derivation trying to illustrate, in particular, the fact that this error on the Outofsample or your test performance can be decomposed into something that can reasonably be called a variance plus a thing called a bias. That's my goal. And once we get there, that's everything I wanted to tell you today. So definitely make sure I go slowly through this.
Can I ask why you call it a variance as opposed to standard deviation? Like variance is a square of
Let me make sure. It will be a variance, yeah.
It is a variance.
And it'll be a variance, and in fact,
The error is also square of
the error is squared, and the bias, I should call it a bias squared.
Squared,
Yeah. Yeah, exactly. It's actually bias squared. Okay.
But you don't want to put that in the title.
What's that? Yeah, a high bias squared. Okay. Let's see. Okay, so now as promised, I'm going to switch notation from calling things an error to calling things a cost. And I still want to keep things as general as possible, so I'm not going to talk about what kinds of models we're learning. But I'm going to imagine that we have a data set. Let's call it D, which is a bunch of XY pairs. And it's generated from some true function, which is for every x, you run it through some f, and x's are generally vectors. This is a set of these. And so the true model, just like we had before, is some arbitrary function. It's not a 10th order polynomial now. It's just some function f that takes in an x sample, adds some noise, and produces an output. And the noise it adds is going to be zero mean unit standard deviation. Actually, no, standard deviation sigma. It doesn't really matter, but okay. So this is where the data is going to come from, and we're going to imagine we have a cost function. Which is a function of the set of y values, and I apologize for what I'm going to do, but I'm going to keep this consistent with the review. There's going to be a model, which is also called f. I don't know why we did this, but it's also called f. But it has a semicolon and then a parameter. If you want, I can call this G, but I'll okay. I'm going to confuse myself, but it's okay. So the model is G, and for every sample x, we're going the model is going to output a prediction, and then we're going to compare it to the y, and the cost function is going to be, we sum over all of the data samples we have, and we look at yi minus g xi theta squared. So we sum up the square differences, and yeah.
Is epsilon also delta correlated? Or
Yeah. Every sample gets its own epsilon. And what we want to do is we want to minimize this cost function. So here, if you think back to the earlier example, imagine f was some third order polynomial, and this is some 10th order polynomial. We have a bunch of parameters. We're going to fit them by minimizing this squared distance. Yeah?
Why is the square distance?
Seems reasonable. We can go into this later, but for today, in some sense, the reason this makes sense is this assumes a model that has Gaussian noise, and the actual model has Gaussian noise. I haven't defined what a likelihood is yet, so I don't want to go that direction. But tomorrow we can talk about it. For now, this is just gospel that a good measure of error is the squared error. And I guess I should emphasize that what we're going to derive today does depend on choosing our cost function to be squared error. But these sort of lessons that you get hold for more general error functions. So if you're doing classification instead of regression, so sidebar, if you're trying to predict a continuous number like a y here, that's called regression. If you're trying to predict a class, like this is class 1 or class 2, that's called classification. So you would use a different cost function if you were doing a different kind of task, or if you're working at some company and your cost function is how much negative how much money you make or something. So the cost function can be defined by the domain. And these lessons that we'll derive hold more generally, but we're going to stick to just the squared error, because then we can really write variance, and it'll actually be a variance and a bias squared. Okay. So what we want to do is take this cost function and find the value of the parameters that make the best predictions. And the way you would do that is just take the argument of this, right? I'm not going to write it all out. And the important thing to keep in mind here is that the value of these parameters here, and I'll write a hat whenever it's a set of parameters that was estimated from data. These parameters that we've estimated depend on the data set. So I should put a sub d because I had some data set, and that's what I fit. Yeah, the parameters inside G, exactly. So yeah, then once we have them, then we can use our G to make whatever predictions we want. Okay, so let's see if I can explain the kind of calculation that we want to do. So what we want to imagine doing is minimize this cost function, get our parameters, and then we want to make predictions on new data. And we want to compute what is our average cost on that new data. So to do that, we're going to need to average over multiple things. We're going to need to average over the ensemble of new data that we get, because we want to know just on average what happens there. And we also, importantly, need to average over the data sets that we get, because we want to know, we don't want our answer to be dependent on this particular realization of the data set. We want it to be, if I learn from this data set and then I test on that data set, on average, what is my cost? Does that make sense? So this is not something you could actually do in the real world because you have one data set, but we can do it with math. Okay. I'm going to start a new one for that. Is there someone under? Excellent. Okay. So what I'm going to write down is the average with respect to the data set, as well as, and I'm going to notate it as an average over the noise when I want to average over the prediction set, because the prediction set is going to have samples of the noise as well. And I want to average that cost function. Just for simplicity, I'll write it like this. Okay. I need another. Okay, so does this kind of make sense? This can be very confusing, so I'm happy to say more words. Yeah, sorry, this means averages with respect to the data, as well as we'll see realizations of the noise. And this might be a little bit confusing, but it'll make more sense when I actually write things out. So first thing is, okay, this is an average of this square difference. G. This is just the definition of C, and again, so this is the notation is bad here, and I'm sorry. In real time, I can't come up with a better one, but that's what's in here. Theta hat again was from the data set that we trained on. Now the yi's and xi's here are a test set data. Okay, so this is really confusing at first, but this is now new data that we want to predict on, because we have our model, we fit it, and now we're predicting on new stuff. Yeah.
So wait, we're averaging over data sets that we've trained on, and then when you're averaging over the noise, you're averaging over the noise of things
The
that
test
we
set.
on?
Yeah.
Okay.
Exactly. Yeah. So maybe a better way of writing it would be over training data sets and test data sets, but that's what I mean by training and test data sets there. Okay. So the first thing we should do is, because this notation is confusing, maybe I'll be really explicit. We can add and subtract the same thing. And what we'll add and subtract is the true function, which we don't know, but it exists.
So your normal x is the training data.
Say it again?
Your x with no I is the test. No, sorry, no.
Oh, I just labeled the samples. Maybe actually, so I'll call the test samples labeled by J. Maybe that will help us. So this is a new set of data. And yeah.
So this is the are you trying to predict or not? This is still a training.
This is now trying to predict. So up here, we had a data set. We, in principle, fit the parameters, and now we're predicting. And in principle, if I didn't put all these expectations in, this would just tell me my performance on my test data set when I use those parameters that I learned on the other data set.
But there's no, when you predict, there's no YJ.
So
YJ.
when I predict, this point here has some xj and yj value, and then this is my g that I fit from this data over here. So these are xi yi pairs. These are xj yj pairs. Yeah. Does that make sense?
But somebody told it. So even though you're predicting, secretly you know what YJ is. It's not you
Oh, so.
you don't train on it, but you know the answer.
Okay, so maybe I should explain the game here. So if you have some experimental data and you want to do this, what you would normally do is you would take some of your data, and that would be the data that you're going to train on, and then you're going to keep some of it secret that you don't look at until the very end, and we're going to test on that, and that's what we're looking at over
Then
here.
we'll go and peek at the data
Yeah.
compared to your predictions.
Exactly. So that's what we're doing here. And then, then when we actually want to go test it on out in the wild, then we might not know the Y's. So you're right. And I guess I should also emphasize here that that paradigm of breaking up the data into different pieces, one that you train on, one that you test on, can be used to optimize your model. You can say, oh, I trained on this one, and then when I test on this one, it does very poor, but when I train this different model on this one and then test on this one, it does better. And you might want to conclude that, okay, the one that did better is the better model and has the performance on a par with what it did over there. But you've actually, at that point, used that testing data to fit which model you want to use. So then you have a third data set often, or a third piece of your data that you use. You only touch it once ever, and then when you want to evaluate the performance of the model. And once you've evaluated performance of something on some data, it's been corrupted, and you can't treat it like it's IID samples from the data generating process anymore. Yeah?
Normally, when you get the data, you're going to divide into 2 normally, or you're going to divide into 3 normally? I got confused on that.
It depends on, so the proper way of doing things is to break it up into 3 pieces. The sets are called the training set, the validation set, and the test set. If you download like the icing model of machine learning is something called MNIST. It's a handwritten digits from the post office. They only have 2. They have a training set and a test set. So I don't want to emphasize the 3 too much, because oftentimes you see that they're only 2. You can make more yourself. From the training set, you can hide some data and use it to evaluate later. But oftentimes, when you download someone's data set, they'll only have training and test set. Yeah.
Yeah. With this, are we trying to figure out how much the training error contribute? What the comparison of the training and test errors? Is that what you're doing?
So.
And like what model?
Sort of. So those are harder questions than I can answer today. I'm just going to try and calculate for you what this red value is, what the out-of-sample error is on average. And the only thing I want to get to is to show you that it decomposes into 2 objects, one that reasonably is called a bias, one's reasonably called a variance. I'm not going to show you this curve or that curve. That's harder.
So I have a question about, so I understand you're averaging, your epsilon averaging is over the testing data set. That makes sense, right?
Yeah.
And then you're averaging over the training data set, which makes you taking different theta values, or you're taking the same theta.
Different theta values. So yeah, let me.
So you're averaging over models also.
Yeah. So what we're not doing is like, it's. I haven't thought about this, but it has the flavor of more of a quenched average than an annealed one, in the sense that you're doing the training procedure, you get your parameters that depend on data, you're evaluating performance, and then averaging that process. Yeah. Whereas I think if you're not averaging the data sets together, because then you'd have more data that you trained on. Okay.
I actually didn't get this. So the expected value on D and E, is it only in testing, training, or both?
Both.
Both. So D are the training data sets.
So only the training, not the testing.
No, first
Yeah.
the epsilon is over testing.
And the epsilon is going to be over testing. It'll be more evident when I write things out.
You're doing both. So
Yeah.
you're calculating a number for each cost, for each model, for each testing data, you get a cost. Then you average over all your testing data sets, and then you average over different parameters that you could have gotten from
No,
the
but I'm confused
Right.
with the notation though, because I thought D was the data sets.
But just the training data set.
Right, but it includes epsilon, right? The way you define
So the training data set did have epsilon in it as well.
Oh, so, okay,
The data set was generated from that same process.
So
But
D is strictly the training data set, and the testing data set,
He's
the only
calling
averaging over.
epsilon.
it's genuinely confusing, so like it's good to talk this through. It'll be more clear when I write out like what we do, but from this stage I apologize for like the way we wrote this.
Enters is really just through theta hat D.
Exactly. The only dependence on data set is through theta hat D. Yeah. Okay, so we added and abstracted the same thing. Now we'll square this bit, and have a cross term. And the first bit here, so maybe this is where things get a little bit more clear. This is the average of the deviation that yj has from f of xj. And I got rid of the average with respect to the data set because, again, that was the training data set, and these j's are the test data. So here, this yj minus f of xj is going to have epsilon dependence. Or we have to average over epsilon because the y's are sampled with meanness, but they have some variance. So we have that. And then we have another term, which is the average over both the data and epsilon of f of xj minus g of xj evaluated at theta d hat squared. And here, I could get rid of the epsilon dependence because there are no yj's here. So I'm going to erase this epsilon dependence. Does that make sense? So there's data set dependence still, but only through here. And then there's a cross term, which I guess I'll write down. Getting short here. So let's go through these. The cross term is easy. So the data set dependence is inside of the G here that I ran out of room writing. But here, the epsilon dependence, when we average this, this averages to 0 because y is on average f, because this is the true model with sample. Yeah.
Yeah. So, but in the first one, why don't you have the d average? F of xj is part of the model space.
No, because that's the
So this is on the test only.
Right, but f is a function defined by the model, so.
No.
So f is the
it
true
depends on
world.
theta. Oh, it
Yeah.
is the true world.
G,
okay.
the g's are the ones that depend on theta. So this one is 0 because this averages to y averages to f. This one averages to whatever this standard deviation of the noise was. And all we have to worry about is this one right here. Is it okay if I write over here? People see this? Okay. So now let's just look at this last one. So let me rewrite it so I see what I'm looking at. We're averaging over the data of the deviation between f xj minus g xj theta d hat squared averaged. Okay. And this is where all the interesting stuff is going to be. So somehow we want to take this and we want to break it up into two pieces that are called a bias and a variance because we didn't get them from over here. This was just a constant term, and this was 0. So we have to do something. Let's do the same trick where we add and subtract something, but what we add and subtract is kind of a weird quantity. Let's add and subtract the average model that we learn over realizations of the data. So that's going to look like this. Okay. F of xj minus average over realizations of the data of the average model that we learned, so g of xj theta d hat, whatever that thing is, let's add it back. And then we had the last bit, which is G. I think I need an extra thing. Yeah, there it is. Okay. So, okay, this is a lot of symbols, but I think I got them right so far. So now if we take just the first bit, what we have is f of xj minus the average squared then we have, from the last two, we have G minus the average of D. Did I write something wrong? Okay, these are this guy squared and this squared, and then there's a cross term that goes to 0. I'm not going to write it out. It goes to 0 because the average model is the model average or something. Because, anyway, you can see it. Essentially, yeah. So that should be okay. So now if we look at these, we should be able to extract some meaning in the context of bias and variance from these two equations. Anyone have any idea which one's bias and which one's variance? It's probably a good way to check that this makes sense. The first one is the bias. And in fact, just to make it simpler, there's no data set dependence here anymore. So let's get rid of this, right? Didn't need to write that. It's just the, and this is a single term, but we should sum over J. So this is how different the true model is from the average model that we learn, right? So this should have some interpretation as a bias or a bias squared. Whereas this one tells us every time we run the learning process, we get a different model that depends on these parameters. And how here this tells us how similar is the model that we learn every time to the average model that we learn over realizations of that. So that's why this is a variance. Does that make some sense? So just to make sure, in the end, we can write this averaged cost function as a piece that has some noise that we can't do anything about, a bias squared, and a variance. And one thing I want to emphasize here, and I realize that we fell into this improper, at least to me, usage of terminology. You should think of this as the out-of-sample or test performance on average decomposing into a bias and a variance term. So you should call this the bias-variance decomposition. Sometimes it's called a bias-variance trade-off, which I don't think you should use because it's possible to have high bias and high variance. It's possible to have low of both, depending on the situation. It's not that by virtue of making one higher, you have to make the other smaller. They don't necessarily have to trade off with one another. So it's better to think of this as decomposing the average test error in terms of these two terms that have some interpretation. Yeah?
I was wondering, so this is now the average test error. For instance, the variance in the error looks like, particularly in terms of the complexity. Because in principle, I'm not sure if that's correct, but one could imagine that for higher complexity, one gets a higher variance in the error. And then the question is, if it's helpful to have a smaller average error but a higher variance.
Or vice versa. Maybe the higher average but a lower variance. Yeah, that's a good point. And it's important to emphasize, I guess, that this variance is this variance with respect to the models that you learn, not with respect to the value of the cost function itself. And we didn't compute the variance of the cost function, just the average. Yeah?
Sorry, I missed how the noise separates out?
That started all the way over here. So we had three terms. One of them was 0. One of them didn't depend on the model anymore. It just depended on the test data, and it was just the noise.
So if we go back to your graph with the red and the blue curve, wouldn't that imply that there has to be actually separation between the red and blue, which is given by the noise term here? Because so you have the bias squared plus the variance, and then you're always going to have the plus the noise, which is a little bit greater than that.
Yeah, I guess that's true. I need to think about this a little bit because you also have noise in the training process also. So I think let me consider this, but we may have drawn this diagram assuming no noise essentially on that plot.
But so
It's not the average, it's not the green, that's why it's the blue line.
Say it again?
The definition of the bias is to the blue line on the bottom?
No,
Or
it's
to the green
it's
line?
to the green line.
The green line. Because it's to the average, it's to the average model or something?
So yeah, yeah, it's Let me think about this. Get back to you. Yeah,
So
not confuse myself.
your blue curve would be this original C that you optimized over.
Yes.
But it's not the same C that you have done.
No. Yeah. The blue curve is this C that depends on the samples xi and yi that we actually use to get the theta. And then this C has yj's, which are new samples that did not get to talk to theta.
So you may want to call the C up there C in and the C down here C out to distinguish.
Yeah. For that notation, that's indeed what I would do. Yeah, I could call. Yeah. Fair enough. Okay. So to summarize, the main lesson that I wanted you to take home today was that whenever you try to fit a model in a machine learning context, what you care about is, as Thierry said, the average value of C out, or the average value of making predictions on data you didn't see, not the data that you trained on. And if this is what you care about, then there are two different kinds of things that you have to worry about, and you would like them both to be as small as possible. And the way that you choose a model and a learning procedure and so on, which we'll talk more about, needs to be cognizant of both of these forces at work when learning. Okay. Any questions on this stuff? Okay.
So this decomposition
Absolutely, yeah.
So and you said that you choose this cost function because you had some Gaussian noise.
Right.
So if you would not have Gaussian noise, all this statement doesn't look true.
Correct. So the exact definition of bias and variance and so on no longer holds. This is strictly for quadratic cost. But you get similar kinds of things for other kinds of cost functions that have a similar interpretation, even though they're different in detail. Yeah.
Bias is mostly about the data set. I mean, can you give me a concise definition of bias?
So the idea here is you live in a million parallel universes, and you generate data in each of them, and then you fit the model in each of them, and then you average all those models together, and you see how different that is from the actual thing that generated the data. And if you were working with a model that was too simple, it would average out to something pretty simple, and it would not be able to capture all the fluctuations in F. If you had a model that was extremely complex, then over realizations of the learning procedure, you would get something that is very, very close on average to the true function. But if you have only one realization of the data set, the problem is that the second term is going to get you, that every time you do it, you'll get a different value for the model that you fit, and this variance quantity could be very high. Yeah.
I'm confused. Like my intuition tells me that, like, suppose I go to look at an infinite complex model over here. So then, I'm fitting perfectly, so I have no bias. I go through every data point.
Mm-hmm.
My model is infinite order. But so now, if I keep taking new data sets to test it on and to train it on, my fluctuations are just going to be fluctuations into the, it's not just going to be a reflection of epsilon, just a reflection of, the reason it varies from set to set is because I'm doing perfectly on every set, but the set is varying. I'm confused why.
That's true, but so you're imagining you have infinite data also? Or sorry, you have a very, very big model,
Yeah.
finite data, and then averaging that realization that many times.
Some of my intuition thing.
Yeah, the problem is hidden in this argument of C here, where this depends on the realization, as you say, of epsilon, and also the choice of the x values that came into that data set. So you could end up getting fluctuations. It's also possible that your data set is so big that even though your model is very big, if you have roughly infinite data, then you will get kind of the same model every time. You will pin it down pretty well, and this variance will be very small. So it is possible with lots of data for the variance to be small and the bias to be small. So I hope this is a helpful decomposition of the test error. And we'll discuss various ways to mitigate these different forces in other lectures. Yeah.
Can you do similar decomposition to show that the Cn is equal to bias minus something?
I haven't thought about it.
Be
I
a
think so,
similar
yeah.
variance,
Yeah, I think so.
no? It'll be a similar variance between, it's just that the bias is a moving target then, right?
I mean, it doesn't seem obvious to me because you minimize over theta, whereas here you don't minimize over theta. So that's interesting.
Right. Yeah, if you re-minimize over theta, then it would be just like a training error again.
Yeah.
Yeah. Yeah, I'd have to think about it. So you're imagining taking that, put in the theta hat there, and then average that with respect to the data?
Yes.
Or, I guess in that case, with respect to...
The expected value with respect to D of this thing minimize, of the C, but minimized, right? So you need to take the mean first.
Sorry, say it again.
You take the min of C, and after that you take the expected value over D.
Yeah, I actually think it's going to be problematic because now you have correlations between
Exactly.
theta and the xi's and y's.
Can you show it's always lower than y squared?
I don't know, maybe.
You have 4 minutes.
Cool. We have 4 minutes. Um,
Optimize that.
okay.
You can give a preview of tomorrow.
I'm curious if anyone has any specific kinds of topics in machine learning that they're interested in, burning questions, requests.
Taking requests.
So I would have a request, but
Yeah.
that would be for the moment I'm gone. But so will you have biological examples of how you apply machine learning in a successful way on some biological system?
I'll have a few,
Okay.
but that's not going to be my emphasis.
Yeah, that's
Yeah.
I also have a request.
Mm-hmm.
You had 2014 paper with Markov.
If we have time, I could spend like half or so of the last lecture on that and related things.
So that's the RG paper?
Yeah, and then there's some other things related to it that I could talk about as well. Yeah.
I don't know if you'll have time to go over GANs.
I wasn't planning on it. So in the space of generative models, the two at the top are GANs and VAEs, variational autoencoders. I was actually going to talk about variational autoencoders and not GANs because my instinct is that VAEs are more likely to be useful in biology.
VAEs are cool.
And they connect to this thing called the information bottleneck, which I could touch on as well if I do that. Yeah.
We were talking about learning dynamics.
In like SGD, stochastic gradient descent kind of stuff. Yeah. So tomorrow I'll talk about that. Yeah.
Isn't that like under methodology restrictions that
With what restrictions?
it's like I don't know if RBMs fall in the context of this, but like within a certain energy requirements.
Like energy-based models?
Yes.
Yeah, I'll talk about that. So, yeah, I'll talk about unsupervised learning in general, and I'll talk about maximum entropy. I'll touch on.
You don't have to talk about maximum entropy.
Did somebody already talk about it?
I think so, right? Stephanie talked about maximum.
Perfect. So maybe I'll mention it for
But
5
you
minutes
can do
and.
RBMs. You
No, but
can
she
do
didn't-
RBMs.
She only talked about Gaussian channel maximum entropy kind of thing, none about
Oh.
general inference.
Okay, I think I'll give. It shows up a lot in inference in biology, so I'll give something about
Yeah.
maximum entropy and connections to other kinds of learning, and yeah, I'll do that. Yeah.
I have two questions. The one is a simple one. Well,
Uh-huh.
but like more overarching question. Like, what I don't understand is people been fitting functions and data, as long as computers exist. So what happened, I don't know, 10 years ago with machine learning? Then all of a sudden, rather calling it fitting, curve fitting, it's not machine learning in its interesting part.
Let me see what time it is, because I want it to be after 3:30 to answer that question. Let me wait 30 seconds. No. The easy part first. Like my shirt, you get all these crazy brandings of AI these days. Roughly speaking, AI means that you're doing either machine learning or statistics, and you want to get money from someone. So let me not use that as.
The atomic clock. Ticking.
Yeah, I'm joking, world. But more seriously, there's a spectrum from like say statistics to machine learning, and it's sort of a continuous spectrum. But roughly speaking, when you're doing statistics, you have very little data, and you're worried about overfitting. Not like being too sensitive to noise in the data. When you're doing machine learning or AI, you're, if anything, worried about underfitting. Like there's so much structure in the data, there's so much richness. that it's hard to find a model that has a high enough ability to fit all the stuff. And then what happened 10 years ago was a couple of things. Computers got a lot faster, data got a lot more abundant, and what people realized is once you have enough data, you can train a certain class of models called neural networks using mostly gradient-based methods. And with enough data, those will perform really well. And 10 plus years ago, the best models were more what are called support vector machines and stuff like that worked really well when you had this sort of like intermediate or small amount of data, but got beaten once you reached this other regime. So roughly, it's just data and compute. There are a handful of ideas that I probably won't go into too much detail about regarding neural networks that are really important. Like these details really do matter, but you're not that far off if you say that what people are doing these days is not that different from what Jan LeCun was doing at Bell Labs in the 80s. Now that we're off camera.
Okay, well, we can take more questions offline. Let's thank David.